Hello, everybody. Welcome to another stream, of my journey learning OpenGL. Last stream, we have concluded the chapters getting started, and we're going to continue with what do you call it? Lightning chapters on this after this stream. So today we're going to get into the colors, how colors work, what colors are. I have some knowledge about this already, but I will try to learn it / explain it like I don't know anything. Okay, let's start. Um, we are not going to change anything, I think, with our code. For now, I don't know. Maybe we are going to. Let's see what happens. Okay. Colors. What are colors? We really used and manipulated colors in the previous chapters. We have set some colors per vertices, but we never defined them properly. Here we'll discuss what colors are and start building the scene for the upcoming lightning chapters. Lightning chapters. What lightning is, what Zeus does, and lighting is what we are going to do. In the real world, colors can take any known color value, with each object having its own colors. Like my jacket, it has blue. In the digital world, we need to map the infinite real colors to the limited digital values, and therefore not all real-world colors can be represented digitally. That's obvious, like all the things in this world. Colors are digitally represented using a green, red, and blue components, commonly as known as in the gamer area RGB. Using the different combinations of these three values within a range of 0 to 1, we can represent almost any color there is. For example, to get a coral, what is coral? Color. Coral, like this, okay. We define a color vector as 1.0. That means the red component is high, the green component is in the middle, and the blue component is in the low area. The color of an object we see in real life is not the color it actually has, but it is the color reflected from the object. So we don't, or without a light, we don't see colors. That's obvious. As an example, the light of the sun is perceived as a white light that is the combined sum of many different colors, as you can see in the image. So this is the white light. It has all the spectrums of the color of the light. So when we sum them together, it is white. Therefore, the color 1.0, 1.0, 1.0 maps to white. And if you would shine this white light on a blue toy, it would absorb all the white colors, subcolors, except the blue color. So the blue color reflects the blue light spectrum, and it doesn't absorb it. This reflected light enters our eye, making it look like the toy has a blue color, and therefore, like if you wear black things in the sun in a sunny day, you would get hot, and if you wear white things in a sunny day, you would not get as much as hot as you get in the in a black clothing, because the black cloth absorbs every color, so every light spectrum, and the white color reflects all of them. You can see that the white sunlight is a collection of all the visible colors here, yes, and the objects absorb a large portion of these colors. It only reflects those colors that represent the object's color, and the combination of those is what we perceive. In this case, a coral color. It is a bit more complicated, but in the PBR. What is PBR here? What is this? physically based rendering. Okay, this is more advanced. Let's see. The light color is white, the toy color is color, and the result is light color times toy color. This is obvious. The light color is and the light color is green. We should only get the green portion of the toy. And if we set, let's read what it has to say. We can set that the toy's color absorbs a large portion of the white light but reflects several red and green and blue based on its own color value. This is a representation of how colors would work in real life. We can thus define an object's color as the amount of each color component it reflects from a light source. Now, what would happen if we use the green light? As we can see, the toy has no red and blue light to absorb or reflect. The toy also absorbs half of the light's green value, because it has 0.5 here, but also reflects half of the light's green value, because it has 0.5. The toy's color we perceive would then be a dark greenish color. We can see that if we use a green light, only the green color components can be reflected and thus perceived. No red and blue colors are perceived. As a result, the coral object suddenly becomes dark greenish object. Let's try one more example with a dark olive green light. Whatever. A lightning scene. In the upcoming chapters, we'll be creating interesting visuals by simulating real-world lighting making extensive use of colors. Since now we'll be using light sources, we want to display them as visual objects in the scene and add at least one object to simulate the lighting form. The first thing we need is an object to cast the light on, and we'll use the infamous container cube from the previous chapter. Okay. For simplicity's sake, we will represent the light source with a cube as well. We already have the vertex data, right? So filling a vertex buffer object, setting vertex attribute points, and all that jazz should be familiar for you by now, so we won't walk you through those steps. If you still have no idea what's going on with those, I suggest you review. Okay, we know. So the first thing we'll need is a vertex shader to draw the container. The vertex positions of the container remain the same, although we won't be needing texture coordinates this time. So the code should be nothing new. Okay, this simply sets the GL position by simply multiplying the position of the object with model view projection matrix. Make sure to update the vertex data and attribute pointers to match the new vertex shader. If you want, you can actually keep the texture data and attribute points active. We're just not using them right now. To light the VAO, because we are also going to render a light source cube, we want to generate a new VAO specifically for the light source. We could render the light source with the same VAO and then do a few light position transformations on the model matrix, but in the upcoming chapters we'll be changing the vertex data and attribute pointers of the container object quite often, and we don't want these changes to propagate to the light source object. We only care about the light cube's vertex position, so we'll create a new VAO. Okay, this code should be relatively straightforward. It is not. Now that we created both the container and the light source cube, there is only one thing left to define, and that is the fragment shader for both the container and the light source. Light color dot object color. The fragment shader accepts both an object color, but this is not okay. This is the backside of the object. This shouldn't reflect the same light. Or whatever. Here we multiply the light's color with the object's reflected color like we discussed at the beginning of this chapter. Again, this shader should be easy. It is easy. Let's set the object's color to the last section's coral color with a white light. What is happening? Set vector object color light color. One thing left to note is that when we start to update these lighting shaders in the next chapter, the light source cube will also be affected, and this is not what we want. We don't want the light source object's color to be affected by the lightning calculations, but rather keep the light source isolated from the rest. We want the light source to have constant bright color unaffected by other color changes. This makes it look like the light source cube is the source of light. To accomplish this, we need to create a second set of shaders that we'll use to draw the light source cube, and thus being safe from any changes to the lighting shaders. The vertex shader is the same as the lighting vertex shader, so you can simply copy the source code over. The fragment shader of the light source cube ensures the cube's color remains bright by defining a constant white color on the lamp. Okay. What I'm going to do right now, I will change the code base. Yes, I will open a new project. Yes. Der graphic document, not this. Okay, go into users documents, theme, childish dev, graphics. This is not it. I have to create a new project here, new project. This should be an empty project. No? I think. This was an empty project, no? I think this was an empty project. Let's see. Empty project, okay. Empty project next, and create lighting. Lighting project, lighting. Solution name is the same. Create new solution. Create it, please. Yes, it. So I will be creating a main class here, and I will also be creating a camera class here, camera.hpp, and a camera implementation, and I will also be creating a primitive like a sphere or primitive.hpp and primitive.cpp. Yes. All right. I will be implementing the camera again here. Or maybe I just look at my code from yesterday. This should be it. Yes. Go into users. Go into documents. Go into stream. Childish dev. Graphics programming. Libraries include util camera. Just once, please. And I also need the shader class. This window. Okay. Okay, you're coming here. what do we have here? Pragma 1, if and define shader. We can simply use our shader code again. I will include it here. Include first IO stream. Hello. Include glad. Glad. So why can't I write GL? Yes. Okay. I was supposed to do the linking. Where was it? In order for our project to use the link, we need link library to our project. And the linker settings supposed to be here in this project. Project name in the solution explorer, and then go to the VC those directories. Properties first, and VC directories, and add. I will add a new solution. Open solution. Open this. Save. Oh, you don't open them in a new window. That's unlucky. Let's open another instance of Visual Studio and open the other solution here. Okay. Should be okay. Now I can copy this and I can go properties, VC++ directories. I can simply copy this, paste it here in the Lightning. Let me get it here. Properties, the directories, copy it, include directory. No. I take this, copy this, library directories, linker, and linker. I would link what? Command line, no. No. Yes, input. I would then copy this into this, apply. Should be all the link. Oh, hello. How are you feeling? This should be the all linking business we are supposed to do right now. Undock this here. Oh, it's fine that you're fine. I hope your day is fine too. Then we include glad. No, it's cool. Okay, my day is also cool. And we define glad. Please, can we define glad? I will restart it. And this, save, and restart Visual Studio. Here, please. Okay, include glad. H. Okay, it's working. We should include glfw slash glfw3.h, and we should include util shader.h. Should also include stb image to load our images. Okay, we included everything, and we're simply going to implement the things we want. And first of all, we're going to implement this header pragma once. We don't want to include anything here, I guess. We're just going to type class primitive, and this class primitive should have vertices from float values, vertices. Did I? So public and expected. Okay, now you do it. Now you do it. Float vertices. The primitive has what else? It has indices. It has vertices, it has indices, and incomplete type is not allowed. Let's ask GPT. Primitive HPP file returns an error. Specifying their sizes. I should define them as as vectors. Okay, of course. So we're going to define them as vectors. Std vector. Of course, we have to include it first. Not even type anymore. Vector. This is a vector from float, and this is vertex. So just copy the next and call it indices. And okay, a primitive should have a color, I would say. Yes, it should have a color. Std, what std? It's a vector tree, so you should include glm. Include glm, glm, vec3 color. And yes, primitive, what should that have? I think more right now, no? Vertices, indices, and colors. A color is actually enough to display it for now. Yes. Okay, so we're going to have three types of primitives. Sphere, a cube, and a... draw it. We can draw it, of course. Draw primitive. It's void. Draw primitive. It doesn't get anything. It's constant, it doesn't change anything. Oh, I don't want to define it. Yes. Draw primitive const. Okay, not found. I will define it later. Yes, draw it. I don't know, what can we say? I don't want to scale it here because I will make it over the transformation in the vertex shader. And draw primitive. Maybe change color. We can do it in the color. Yes, I think this should be it. Yes. And yes, this is our primitive. We can implement it here. We should type if and def. If not defined, primitive h define primitive h, and we should type end if here, and if. Yes. Okay, this should be it for the primitive class, and we should include primitive HPP, and we should call class sphere is a primitive. How can we define a sphere? How can we draw a sphere? Draw sphere OpenGL sphere. We're going to need indices. How much? How many indices do I need? This is too much, man. Maybe I shouldn't have done this. Maybe I shouldn't have done sphere. See. Oof. I don't want to read all of it. Okay. Let's scratch sphere for now and call cube primitive. Cube and a triangle prism. Triangular prism. OpenGL. Triangular prism. I should open a paint. The triangular prism should have these vertices. A vertex here should bind this and this. It should bind and this. So these are okay, and we should determine this. We want to, yes, we want to have a regular triangular prism, so this length should be equal to this length. But I'm going to define the cube first. The cube should have the vertices of vertices like this. So this is the 0. Cube should have a vertex here, 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 here. You know what I'm going to do? I'm simply going to open Blender. I will create this here, the cube. I will simply export this cube as an object file in stream, in assets. And I will create a new folder here called objects. Import it. I just created it, and yes, objects, and I should be able to read it here. Edit with Notepad++. No thanks. So the vertices are here, as you can see. This spans from 1 to -1. And what is this? This is V. This is vertex. It should be vertex. As 1, 2, 3, 4, 6, 7, 8. There are 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8 vertices. So these are the vertices. These are the vertices. And how is it drawn? Go into edit mode. I want to see the triangles. Toggle X-ray. Oh, these aren't triangles. Or these are rectangles. So we can also draw rectangles, I think. Close the Blender now. Don't save. Draw rectangle. OpenGL. OpenGL draw modes. Draw modes. Draw elements. Where are the modes? Come on. There are points, lines, line strip, line loop, triangles, triangle strip, triangle fan, triangle fan, triangle fan. There are every possibilities but quads. So we are going to use triangles with these vertices we have here. Float vertices array equals to this with following vertices. Choose the V. Okay, and top this. on top these. Okay, and also this. Yes, and we're going to add commas here. Minus here, and every one of them. Add one F here. Also this, this. Delete them all. Add F. Too many initializer values. Does that even mean? Come on. Initializer values. Of course, there is no array thingy here. What do you mean here? So this should go like this, primitive. A method vertices equals this. Like this, no? Expression must be viable. So this should work like this, huh? It doesn't work. What is this? Into this classes. Know how to create an object. I don't know. I know how to call methods. These are. I know what these are. Structure parameters. I know what these are. Access specifiers. Private. Okay. Encapsulation. OE. Public, private. Okay. This we know. Inheritance. Vehicle. Car. Public vehicle. Class vehicle. Public string brand. Ford. White honk. Toot toot. Okay. Class car. Public vehicle. All inheritance. Okay. So call class here. Class native. Public class primitive. Should have don't have any. cube. Cube. Okay. Let's ask the guy, generate me two classes. One of them should be a an header file with method declarations, file. Yeah, header file with the method declarations called primitive.hpp. Declarations like primitive or vertices. This is called primitive.hpp, and the other file should then create sub primitives like cube, triangular, prism, and implement the method or corresponding primitives. Primitive has a public constructor, has a virtual void. Raw primitive method, it's the const. It has getters and protected. It has vertices color. And the other primitives, CPP, has primitive as the constructor, and vector primitive get vertices, indices. Okay. Can't I write the primitive classes into the primitive? Primitive.cpp. So we should maybe create a constructor here. Weird. Should be like this. Weird, that's so weird. Primitive. Don't know. To get code array. Also code array. Primitive. do we have thing and the class cube and public a cube void diff const override does then we create a cube. So cube of void cube draw as a method implement this. Oh. And afterwards you're defining a triangular prism as a primitive public triangle prism void draw if const. So the prism this is really different from Java. Alright, man. Virtual. Okay. Now we can type it right. Okay. And what happens if we type these in? That also work? Yeah, that's what I had to do. Okay, I get it now. And yes, the cube should be created. Zero. That maybe. Okay. Okay, I can change it. So I will switch back to vector again. std vector float vertices the vector of float vertices and does it have this word and have this and in place and I in place No. Shit. Okay. I lost the vertices. Fuck. Let's just place back, append, add, sign, push back, pop, add, sign, clear. What is push back? So we are just going to push all the vector vertices in. This is LM vec3. This is such a drag. One. Goats. I would say this, I don't care. Find integer. Integer. Like this. Push back 50. No. Push back 4, 5, 6, 8. I -1 here. 1, 1, 1 here. And 1, -1 and -1, 1, so -1, -1, -1, 1, 1. This should be -1, -1, and 1. These are vertices. The indices should be then like this. Back. ELM. vec3. First triangle. So the paint, triangle. Have 1. So ix 1 with minus z and plus z. So the 1 is here, -1, x and y is here. So the first vertex is in the back. So the first vertex should connect it. So the second vertex is somewhere here. And the third vertex then somewhere here, the in the front, like this, somewhere here, and the third vertex is the fourth vertex then should be here. 1 and -1 and 1. So we should connect this is number 1, numero 1, numero 0, numero 2, numero 3, numero 4. So we should 3. We should connect 0, 1, 2 for this, and 2, 3, 1, 0, 1, 2. Two, 0, 2, 3, 1. Yes, 2, 3, 1. Afterwards, we should. How does he create the cube here? The basic, getting started. So here it is still a 2D square. It creates it in coordinate system going 3D. Sorry. To render a cube, we need a total of 36 vertices, 6 faces. What the link? Okay, I'm kinda bored. I will edit here. Thanks for joining. See you in the next